Greetings students, this is 5th online lecture of solid state physics. In this class, we are going to discuss about stress-strain curves and analysis of elastic strains. After this lecture, you will be able to understand elastic strain, elastic waves in crystals, uniform and non-uniform deformations, and essential strain components. Analysis of elastic strains. At first, let's discuss about a few basics of stress and strain with the relevant stress-strain curve. Stress, its force per unit area. It's denoted by sigma. So sigma is equal to force per unit area. It's measured by the unit of Newton per meter square, where sigma is the stress applied and F is the applied force, A is the cross-sectional area experienced by force. Tensile stress. Actually, the stress are of two types. Those are tensile stress and compressive stress. Tensile stress, it's the force applied per unit area which results in the increase in length of a body. Objects under tensile stress become thinner in perpendicular to the force applied direction and longer along force direction. Compressive stress is the force applied per unit area which results in the decrease in length of a body. The object under compressive stress becomes thicker, that means bulge in perpendicular to force direction, and shorter, that is compressed along the force direction. In the picture shown, we are seeing the object before and after applying force. When the force is applied on the object undergoes either compressive strain or tensile strain, depends on the direction of force applied on the object. In this picture, the object is pulled externally by a tensile stress and hence there will be tensile strain in the object. Strain is known as the amount of deformation experienced by the body in the direction of force applied with respect to the initial dimensions of the object. Strain is denoted by epsilon, which is equal to delta L divided by L. Delta L is the change in length per L is the original length, where epsilon is the strain caused by the applied stress, delta L is the change in length, L is the original length of the object. Strain is a dimensionless quantity. Strain is also of two types. Those are tensile strain and compressive strain. Tensile strain is the change in length in the direction of applied force of the object by the application of tensile stress. Compressive strain is the change in length of the object by the application of compressive strain. In these pictures, the tensile strain and compressive strain by the application of tensile and compressive stress are shown. When the tensile stress is applied, the object becomes longer in the direction of force and thinner in the perpendicular direction of the force applied. In the down picture, the compressive stress is applied. The object becomes thinner in the force applied direction and thicker in the perpendicular direction. Here, tensile stress is taken as positive and compressive stress is negative. Stress for anisotropic medium. Let's consider cube on which stress acting along 3 axes with 9 components. 3 are normal, 6 are shear stress components. Stress with 3 components as vector with sigma equal to sigma suffixes ij. Collection of all combinations is stress tensor. Stress has 9 components. Here actually J represents the directed force pushing along an interface of constant I. Vector has one component in a particular direction, whereas tensor has more than one component along in a particular direction. For example, along x-axis, if we have x1, x2, x3 and so on, then we need to represent by tensor and not by vector. A scalar is a 0 rank tensor, a vector is a first rank tensor, matrix is a tensor of rank 2 and so on. This picture representing all the 9 stress components acting on an anisotropic medium, that is crystal. You can see the stress acting along x, y and z axis. There are 3 mutually perpendicular stress acting along all 3 directions on each plane, such as sigma xx, sigma xy, sigma xz acting on a face in yz plane, and the stress components sigma yy, sigma yx and sigma yz phase in xz plane, sigma zx, zy, zz phase in xy plane. For example, here yz phase is pointing along x-axis. In the 2 subscript letters, the first letter indicates the direction of the normal to the plane or face under consideration. That is, orientation of the face that indicates in which direction the face is pointing. And the second indicate the direction of the components of stress, that is, direction of the force. For example, here we have sigma xx, sigma xy, sigma xz. In these 3 stress components, the first letter x indicates the direction of the face normal to the yz plane. And the second letter, that is x, y, z in each of these elements represent the direction of components of stress respectively. The element sigma yx is acting on the face in xz plane. Here y represents normal to the face in xz plane, indicates the face is pointing along y-axis, and x represents the direction of stress which is along x-axis. In this, you can notice stress components along x, y and z axis. Along x directions there are sigma xx, sigma yx and sigma zx components. That is, more than one components are acting along x-axis, and similarly you can check all other components corresponding to y and z axis. And that's why stress elements are represented by tensor. The plane shear components sigma yx is equal to sigma xy, sigma yz is equal to sigma zy, and sigma xz is equal to sigma zx. These shear components are equal to each other, so in total only 6 stress components are needed. Actually sigma xx, sigma yy, sigma zz, and in addition to that the cross stress components are sigma xy, sigma yz and sigma zx. So these 6 components are sufficient to describe stress. Shearing stresses on any side of the cubic element are taken as positive. So stress on a volume element within a solid is a tensor given by a matrix. As indicated in the matrix, all 9 different tensor components are possible for the cubic volume element. So here sigma equal to the 9 stress components are indicated: sigma xx, sigma xy, sigma xz, sigma yx, yy, yz, sigma zx, zy, zz. So in nutshell we can say sigma equal to sigma ij, and here I represents orientation of the surface and j represents the direction of the force. Here you can check all the 9 components of stress in the matrix, but sigma xy is equal to sigma yx. Similarly, the other off-diagonal components are equal, and hence there will be 6 unique stress components sufficient to describe stress on cubic volume. So here sigma ii represents sigma xx, sigma yy and sigma zz along all the 3 axes, and this represents the tensile or compressive stress on the cubic volume. And sigma ij, it represents shear stress, that means sigma xy, sigma yx, sigma zx, sigma xz, sigma zy and sigma yz. These represents shear stress. And here sigma ij, which is equal to sigma ji, and that's why we need 6 stress components to describe the stress. So now let us discuss the stress strain curve. In this stress strain curve, when the load is increased, there is elongation in the rod. Suppose a rod is connected with a load. So when the load is increased, there will be elongation in the rod, and it's completely reversible within elastic limit. So when the load is increased, that means stress is gradually increased and strain will also be uniformly increased. And this is up to the elastic limit. So within elastic limit, when the stress is removed, the object is going to be completely reversible. So this is within the elastic limit. So when the load is removed, the rod or wire come back to the initial position. So within this limit, we call it as the material is under elastic behavior, and when the stress is increased, the strain is uniformly increasing and the line is linear until A. So until the point A, the slope is linear and the deformation is elastic. So the slope follows the stress by strain proportionality. Above the point A, the stress strain is no longer linear and it's called a proportional limit. It's called as proportional limit. So the length of the linear region up to which the material shows stress strain constant proportionality, which is called as the yield strength of the material. If we increase further load, the material takes a curvy path as shown in the figure. That is, the strain is increased even for a small increase of load, but the object is still within the elastic limit. When the load is removed, the object comes back to the initial position until the point B. This point is called as elastic limit or yield point. So in the region OB, the material has elastic behavior. Up to OA, the material follows linear line and the slope is constant. Stress by strain is constant. So this is called the proportional limit. And up to OB, the material is under elastic limit. So up to the point B, if you increase the stress, the strain will be uniformly increasing but slightly higher strain after the point A. But even though the material can come back to the initial position when the stress is removed. If we increase the load beyond this point, suppose if we are increasing the stress beyond the point B, then the strain abruptly increase up to the point D. But when the load is removed from the rod or wire, the object can't come back to its initial position. The object is left with the elongated position, which is called permanent set. For example, if we increase the load up to the point C, and then when we remove the load, the object will be left with the permanent set position as shown in the picture. When the material is close to the point D, it will undergo too much thinning, and this point D is called as necking, up to which the material can withstand with the load. The length of maximum strain up to which the material can withstand load without breaking, that is up to the necking point D, is called the ultimate tensile strength of an object. However, the material will be at permanent set and it can't be returning to the initial stage. That should be noted. Once we start to increase the load after this point D, the material undergoes large increase in strain, which leads to fracture at the point E. If the points D and E are close enough, then we can say something about the material. That means the material has a brittle nature. For example, ceramic and glassy materials. If these points D and E are far apart, the material has ductile nature. If D and E are not close, then the material has ductile nature. For example, steel, gold, silver, etc. So these metals have the ability to receive permanent deformation without fracturing. The material which can withstand up to the point DE determines the fracture strength. Up to the point E determines the fracture strength. In summary, in OA region, the material stress is proportional to strain. AB is curvy and B is known as elastic limit. In BD region, the material has plastic behavior. DE region determines the fracture or brittleness of the material. So the material undergoes different stress strain properties when the load is increased. The region OA and up to B is known as elastic deformation. AD region is uniform plastic deformation. The total OD region is uniform deformation region. DE is non-uniform plastic deformation, and the overall region OE, O to E, is called as total elongation of the material. The right side picture of metal rod shows material nature under different loading conditions. So let's now discuss on elastic strains in anisotropic medium. Elastic strain, it's actually the limit of elasticity up to which the object rebound and regain to initial condition when the load is removed from an object. When the stress exceeds the yield limit or elastic limit, deformation happens. Elastic properties of crystal is uniform when the crystal medium is homogeneous. So these points are as we discussed. We consider the elastic properties of a crystal viewed as a homogeneous continuous medium rather than as a periodic array of atoms. So we consider the medium as a homogeneous continuous medium. The continuum approximation is usually valid for elastic waves of wavelengths lambda longer than 10 power minus 8 centimeter, which means for frequencies below 10 power 11 or 10 power 12 hertz. Here the continuum approximation, it's a mathematical idealization for modeling the collective response of discrete systems. For example, let's take a solid as continuum and ignore all the lattice atomic details or the individual atomic position. The figure is shown below. You can see it's a solid, and we consider this solid as continuum. That means we ignore all the lattice atomic details. We consider average atomic position in a certain region of one-dimensional solid. This approximation is known as continuum approximation. Let's take a region, for example, here between x and x plus dx with the length of dx. This is the region of our consideration in which the average interatomic distance is smaller than the equilibrium separation. In other words, atoms are compressed or far apart in this region as compared to equilibrium separation in the rest of solid. So we can assume that the atoms are either high dense or less dense in this region as compared to the rest of solid. If this disturbance in a small region is created in a solid, it won't stay in a particular region because of the restoring forces of the solid atoms. This disturbance would propagate in a solid. This propagation is called as elastic waves in solid. These are the disturbances of the density of the solid. So the ions or atoms undergo compression or rarefaction, and hence there will be variation in the ion or atomic density of the solid, which propagates across the solid. This wave is called elastic wave. We assume longitudinal wave since the disturbances of atoms from the equilibrium position is propagating along the direction of disturbances. So this elastic wave would have a certain wavelength if it has to propagate along a solid. The continuum approximation could be valid if the wavelength of elastic wave is much greater than that of atomic distances. By assuming the atomic distance is in the order of 10 power minus 8 meter or 1 angstrom, we are taking the wavelength of elastic wave as lambda is greater than 10 power minus 8 meter. The elastic displacement at the atomic position or certain location x is u of x. Here u of x is the average displacement from the equilibrium position at a certain location x. So u of x is a wave parameter that represents wave amplitude. When the elastic displacement is small enough, we can use Hooke's law. That is, stress is directly proportional to strain. This is valid. There is a variation in the atomic position. So the displacement per unit distance can be represented as strain. So there should be strain in this particular distance. Strain can be denoted as E. So E is equal to strain, which is du by dx. So there should be force acting per unit area in this region of one-dimensional solid. So stress sigma, which is equal to force per unit area. For this stress there will be strain. That means the disturbances in the density of the solid. The basic physical ideas are simple, which we are using in this calculations. So we use Hooke's law and Newton's second law. Hooke's law states that in an elastic solid the strain is directly proportional to the stress, as we already discussed. So F by A is proportional to delta L by L. The law applies to small strains only, that means infinitesimal strains. We have seen that we are in the nonlinear region when the strains are so large that Hooke's law is no longer satisfied. So Hooke's law is satisfied only in the small or infinitesimal strains. As we already discussed in the stress strain curve, up to certain limit the material could have elastic nature. We specify the strain in terms of the components E suffix xx, EYY, EZZ, EXY, EYZ and EZX, as we already discussed, so which are defined below. We treat infinitesimal strains only. So here we consider infinitesimal strain in solid for which Hooke's law is valid, as we already discussed. So we shall not distinguish in our notation between isothermal and adiabatic deformations. The small differences between the isothermal and adiabatic elastic constants are not often of importance at room temperature and below. So we imagine that three orthogonal vectors x, y, z of unit length are embedded securely in the unstrained solid, as shown in the figure. The figure will be shown in the next slide. So without deformation, it will be x equal to epsilon xx into the orthogonal unit vector and epsilon xy y cap plus epsilon xz z cap, and y could be represented as epsilon yx x cap, epsilon yy y cap plus epsilon yz z cap. Similarly for z. And let's take the dot product of x, y and z. So here x dot x, that gives epsilon squared xx plus epsilon squared xy plus epsilon squared xz. Similarly y dot y and z dot z. Here we are taking the dot product. It's because the dot product gives the information about how much of the force vector is applied in the direction of the motion vector. So the dot product measures the angle formed by a pair of vectors and the position of a vector relative to the coordinate axis. This picture shows the object under stress and the corresponding strain before and after deformation. The stress components are acting on an anisotropic medium. Due to the stress applied, there are changes in orientation and length as shown in the figure. We consider only infinitesimal changes in the strain in order to estimate the strain components as discussed earlier. Here the deformation is uniform, that is, for equal stress there will be equal strain in the solid object. After a small uniform deformation of the solid, the axes are distorted in orientation and in length. In a uniform deformation, each primitive cell of the crystal is deformed in the same way, as discussed in the earlier slide. The new axes x prime, y prime, z prime may be written in terms of the old axis. So x prime is 1 plus epsilon xx plus epsilon xy plus epsilon xz, and similarly y prime and z prime as represented in the slide. Here the strain tensor is represented by a matrix which has 9 components. So a matrix is given E with suffix ij. So here I and j are x and y components. So here exx, exy, exz. So it's given in the matrix form. So after infinitesimal strain, the diagonal distortion takes place as seen in the matrix with 1 plus EII. that means the diagonal distortion. If both the surfaces are same, then the derivative would be the change of displacement along certain direction. Let's say along x direction divided by the length of the cube along same x direction. Also, if we take the mixed indices, we can take the displacement along x and unit change in length along y plus displacement along y direction per unit change in length along x direction. So it's given here e with suffix ii, which is equal to dou ui divided by dou xi. This is representing the change of displacement u along x direction per divided by the length of the cube along x direction. So this is for EII, same indices. But if we have mixed indices, EIJ, in such case dou ui divided by dou x suffix j plus dou uj plus dou x I. So in this case, the displacement u along x direction divided by the unit change in length along y direction plus the displacement of u along y direction divided by unit change in length along x direction. So this is for the strain for with the mixed indices. So here Eij, where I equal to j, that represent linear strain, and if I is not equal to j, that represents shearing strain. So the linear strains are given in diagonals, and the shearing strain components are off diagonal components like epsilon xy, exz, eyx, eyz, ezx, ezy. These are off diagonal components, and these represents shearing strain, and the diagonal components represents linear strain. So here Eij, which is equal to Eji. So again, similar to stress components, we have 6 unique components to define strain. So instead of tensor, now we have made it as vector with 6 components because some of these elements are repetitive. So the coefficients epsilon, alpha, b define the deformation. So they are dimensionless and have values less than 1 if the strain is small. The original axes were of unit length, but the new axis will not necessarily be of unit length. That is, x prime is greater than or equal to 1. As already discussed, in order to find out the position of a vector, let's carry out dot product of the position coordinates x prime dot x prime for the case of after deformation. So this is given in the equation, and x prime dot x prime, that becomes 1 plus epsilon xx the whole square plus epsilon squared xy plus epsilon squared xz. And finally we have with a plus b the whole squared, we are expanding. So x prime dot x prime, that gives 1 plus 2 epsilon xx plus epsilon squared xs plus epsilon squared xy plus epsilon squared xz. And by omitting the higher orders of strain, that means the epsilon squares, then we get x prime squared, which is equal to 1 plus 2 epsilon xx. So x prime is square root of 1 plus 2 epsilon xs. So by using binomial theorem, if we expand, so we get x prime equal to 1 plus epsilon xx to the first order only. So this is just the first order, and the higher order terms of strain we are neglecting. So similarly for the case of y prime dot y prime and z prime dot z prime, we have got the expressions. This picture shows the object under uniform deformation, before and after deformation, and this is uniform deformation. The stress components are acting on an object that undergoes strain. The strain is uniform along x, y and z axis. In uniform deformation, each primitive cell of a crystal is deformed in a same way. Let's consider an atom situated at a point R before any stress applied. This atomic position vector can be expressed as R equal to xx cap plus y cap plus z cap. When the stress is applied, this atom is relocated to a position R prime as shown in the figure. The position vector can be expressed with the position coordinates as R prime equal to x prime plus y prime plus z prime. So the atom undergoes displacement by the application of stress. This displacement of an atom is given by capital R, which is equal to R prime minus R. As discussed, when stress is applied, the cube undergoes deformation in both orientation and length, that is tensile strain and shear strain. At first, let's discuss about the tensile strain with this figure. The figure shows the object under uniform deformation. Suppose, let's assume that the object undergoes infinitesimal strain in length. Before deformation, the plane position is A, B, C, D. After deformation, the position is changed to A prime, B prime, C prime and D prime. So, after deformation, displacement of A in x-axis is U and along y-axis is V. At the point B, after deformation, the displacement is U plus du by dx into dx. Similarly, at the point D, the displacement is V plus dv by dy into dy. So the strain in the element AB along x-axis is E with suffix x, which is equal to du by dx. Similarly, the strain in element AD along y-axis is Ey equal to dv by dy. So the tensile strain is positive if there is elongation in the element and negative in the case of contraction. For three-dimensional case, let's take U, V and W as displacements along x, y and z axis. Suppose dx, dy and dz are the edges of the unit cell. Then the strain Exx is equal to du by dx, Eyy equal to dv by dy, Ezz equal to dw by dz. So Exx is equal to du by dx into dx divided by dx, which gives du by dx, and this is normal strain or longitudinal or otherwise tensile strain. The picture shows the object under shear strain. Shear strain represents total angular change in the object. The orientation will be changed here, and in the figure A, B, C, D are the original element which is deformed to A prime, B prime, C prime and D prime. So in this picture, A, B, C, D is the original element. After deformation, the point A is displaced to U along x-axis and V along y-axis. Let the point B is displaced along y-axis by V plus dV by dy into dy, and along x-axis it is U plus du by dy into dy. Similarly, the point D is deformed along x-axis by U plus du by dx into dx, and along y-axis V plus dv by dx into dx. Shear strain is positive if the right angle between the two positive axes decreases, and negative if the angles are increasing. So here EXY, that means the strain with the crossed indices, that represents the sum of the two angles, that means alpha and beta. So alpha plus beta, that gives du by dy plus dv by dx, which is also equal to E with suffix yx. So in this case EXY, which is equal to EYX. So these strain components are equal. So from both the tensile and shearing strain discussion, we can conclude that the components of strain are Exx equal to du by dx, Eyy equal to du by dy, Ezz equal to dw by dz, and Exy, this is alpha plus beta, that means du by dy plus dv by dx, which is equal to Eyx. And similarly for the case of Eyz, this is dv by dz plus dw by dy. This is also equal to Ezy. And Ezx, in this case dw by dx plus du by dz. This is equal to Exz. So there are 6 components required to define strain. And here alpha is dou u by dou y and beta is dou v by dou x, the angle. For example, x prime dot x prime, this gives 1 plus 2 epsilon xx plus epsilon squared xx plus epsilon squared xy plus epsilon squared xz. This equation we have already discussed. So when x prime is equal to 1 plus epsilon xx, by omitting the higher order strains, the fractional changes of the orthogonal vectors x, y and z length of the axis are epsilon xx, epsilon yy and epsilon zz respectively to the first order. So ignoring the product of strains. So here an unit length is increased along all the 3 axes. By omitting higher order of strains, we have this equation. In order to discuss the effect of the deformation, equation 1 on an atom originally at r equal to x cap plus y cap plus z cap. This we discussed in the earlier slide. So the origin is taken by some other atom. If the deformation is uniform, then after deformation the point will be at the position r prime. This is obviously correct if we choose the x-axis such that r equal to x cap, then r prime equal to xx prime by definition of x prime. So the displacement r of the deformation is defined by the deformation vector. The deformation vector r equal to r prime minus r, that means the displacement. So this can be estimated by this x r prime and r values. So the deformation vector r is equal to the second equation, that gives the second equation, and at uniform deformation for equal stress there will be equal strain. So r from equation 1 we get the equation 3. R of r equal to x epsilon xx plus y epsilon yx plus z epsilon zx into x cap and so on, as mentioned in the equation 3. So in this picture, let's discuss a solid material which undergoes non-uniform deformation. The atomic position R is shown here as discussed before. Let's consider a non-uniform deformation when the stress is applied. As we already discussed, under non-uniform deformation, the strain is no more uniform along x, y and z axis. As shown in the figure, there will be change in geometry of the sample of for the application of stress. there will be changes in the local strains. Here let's consider the origin of the atomic position R is close to the deformed position of the atom. The dislocated atom is at R prime. Since the positions of the atom before and after deformation is very close, the displacement R is 0. That means R prime minus R equal to 0. So R with respect to the position of the atom R, that means the capital R with respect to the position of the atom, that means the small r is equal to 0. That means R of R equal to 0, since these two positions are very close. So let's start from the equation 3 as shown here. So equation 3 is given. This may be written in a more general form by introducing u, v, w such that the displacement is given by for an atom, that is R of R equal to u of R x plus v of R y plus w of R z. Here u displacement along x axis, v along y axis and w along z axis for uniform deformation. These things we have already discussed in the earlier slides. And if the deformation is non-uniform, we must relate the displacement along x, y and the z axis. That means u, v, w to the local strains, because it's a non-uniform if we consider. Then we take the origin of R close to the region of interest as discussed in the earlier slide. So at the deformed position, R prime is very close to the original position, so R prime minus R gives 0. Then comparison of equation 3 and 4, that gives as by Taylor series of expansion of R by using R of 0 which is equal to 0. So we get x epsilon xx by comparing equation 3 and 4. We get x dou u by dou x and y epsilon yx which is equal to y dou u by dou y, etc. So this gives the equation 5. And here we know that epsilon with suffix xx is dou u by dou x as discussed from the earlier slides. So it is usual to work with coefficients E alpha beta rather than epsilon alpha beta. So instead of epsilon alpha beta, let's take E alpha beta. We define the strain components Exx, Eyy, Ezz. That means the diagonal strain components by the relations using equation 5. So we get Exx which is equal to epsilon xx, yeah, both are same, which is equal to dou u by dou x, and Eyy which is equal to dou v by dou y, Ezz which is equal to dou w by dou z. And this represents the displacements of u, v, w with respect to x, y, z respectively. The other strain components, those are Exy, Eyz and Ezx, and these are defined in terms of the changes in angle between the axes. So using equation 1, we may define Exy equal to x prime dot y prime which is equal to E or otherwise epsilon yx plus epsilon xy which is equal to dou u by dou y plus dou v by dou x. These things we already discussed in the earlier slides by the summation of alpha and beta angles. So alpha plus beta, that gives this one. And similarly for the case of Eyz and Ezx, so collectively we have got the shearing strain components. That means the sum of the direction of strain components we have got, and strain in xy direction, this is equal to the partial derivative of u and v with respect to y and x respectively. So here the strain in xy direction is equal to the partial derivative of u and v with respect to y and x respectively. As already discussed, the strain with mixed indices is equal to the sum of angles of alpha and beta, and the coefficients of epsilon ij or epsilon alpha beta, where I equal to j or alpha equal to beta, that defines linear strain. that is diagonal elements, and epsilon ij where I is not equal to j, that means x is not equal to y, that means x and y are not equal, right? Or otherwise we will have epsilon xy, epsilon yx, epsilon xz, such components. So the mixer indices that represents the shearing strain, and that is off diagonal elements. So we may replace the sign, and if we neglect the terms of order epsilon squared, we get the six dimensional coefficients, the values of six dimensional coefficients as represented in the equation 7. So that is epsilon alpha beta, which is equal to epsilon beta alpha, that completely define the strain. So here epsilon xx, which is equal to epsilon yx, and epsilon yz equal to zy, and so on. So in matrix representation we can see all the 9 components of strain as that of stress. But since the off diagonal pair of elements are equal as discussed, we have 6 on and off diagonal coefficients to define strain. So in nutshell, we need the 6 dimensionless coefficients epsilon alpha beta or epsilon beta alpha to completely define the strain. So far we have discussed about analysis of elastic strains in detail. Hope you would have understood the concepts of stress strain curve, elastic waves, stress components, deformation of an anisotropic object, uniform and non-uniform deformation conditions, displacement of atom, normal and shear strain, and the strain components that define orientation and length of the object in all 3 axes. Students, hope you would have understood the concepts. In the forthcoming lectures, we are going to discuss about the crystal vibrations, thermal properties, free electron, Fermi gas, and energy bands. Stay tuned. So this is the reference book used, Introduction to Solid State Physics by Charles Kittel. Students, until the COVID situation changes, stay at home, wear mask, and sanitize your hands when you are going out, and stay safe. Have a great day. Thank you.